This video is for Math 1325. Today we're going to be working on section 7.3. But before we do that, let me go back real quick to one last problem in section 7.2. Problem number 10. I made a little mistake at the end when I had this negative 750 right here. I also added a 1 over negative 750 to the outside. That was wrong. That shouldn't have been there. So what happens is it gets a little more confusing when we had all these fractions here and all this extra numbers. Usually it isn't as messy as this, but you need to pay attention to one of three things always happens. Sometimes when you pick out your u substitution part, sometimes when you do the derivative of it, it's entirely what you need, and there's no adjustment needed at that point. Sometimes the du part is already in the original problem, and you're all good to go. That's the easiest kind. But the other two cases are sometimes there's an extra number here, and maybe in a hidden way like this 750, or sometimes there's an extra number here. And that makes a difference which one it is. So if you go back to number 6, in number 6, I set the denominator part equal to u, except for its exponent. I set the denominator equal to u, and the derivative of it did not exactly equal what was here, but it was only off by a constant. I could factor out a 2 from this du part, and taking the 2 out left exactly what was there. But I've got the extra 2 over here in the du part. When the du part has an extra constant, that's when you have to insert it here along with a 1 over it. But sometimes the extra constant is already here and not over here. That's what happened on number 8. Number 8, after I picked out my u substitution, I did the derivative of it, simplified it, and what remained was here, but there was an extra 28 over here. When the extra constant is in the problem, then you just pull it out to the front, and there is no 1 over going on. That's what I was supposed to do on number 10. I was just getting, it took a little work to figure out what the extra constant was, so I wasn't paying attention at that point. But I should have realized that this negative 750 right here was an extra constant in the problem. It wasn't an extra constant in the du part. So that means you just pull it out and there wouldn't be a 1 over part. And that's the one mistake I had at the end, was I had an extra 1 over 750 that shouldn't have been there. So let's just do number 10 one more time so you can see a clean example of it. So I just hit try another. And here's my derivative function. P prime of t is 500t times e. P prime of t is 500t times e. Times e to the negative t squared over 4. So because derivatives and antiderivatives of e to the whatever exponent you have are easier to do, that's why the best substitution plan here would be to set the exponent of the exponential. That's what you want to set equal to u. And that way, I'll write this out first. So this is the integral I would like to do. I'm going to set this entire exponent equal to u, because then I'll end up with an e to the u. I'm hoping to end up with an e to the u. If this complicated part, if that was simpler and it was just u, then this would be easy to do. So set the complicated part equal to u, and then the derivative of it happens to be negative 2/4 t to the first, or negative 1/2 t to the first. And because this side's about t, that's why there's a dt here also. But if you do the the exponent times a constant, 2 times negative 1/4 is negative 1/2. And then decrease the exponent by 1. So the issue is I don't have exactly what's here. I have the t and the dt, but I have a 500 instead of a negative 1/2. So it looks like it's going to come out the same here as it was supposed to last time. It turns out that negative 750 times negative 1/2. No, I guess it isn't the same. It's negative 1,000. Negative 1,000 times 1/2 is how you get positive 500. And you could just make this an algebra problem and say what times the needed negative 1/2. What times the needed negative 1/2 is going to get me 500 is what I'm trying to do here. So that's why you multiply by negative 2. And the missing amount is negative 1,000. So I can think of 500 as negative 1,000 times negative 1/2, but the negative 1,000 is extra. Now we have the extra part in the problem. When the extra constant is in the problem, you just pull it out to the front. That was the mistake I made last time. I was thinking that the extra constant was coming from du, and it wasn't. So that's the du part right there. The negative 1/2 will go along with t and dt, and that creates du. So now we have it where everything's covered except for the extra negative 1,000, and you just pull that out front. The integral of e to the u is e to the u, so that's why we wanted that to happen. And you can just bring the constant along for the ride, plus c. And then we can plug the stuff that was set equal to u back in. So the answer to this in general is negative 1,000 times e to the negative t squared over 4 plus c. This would be the generic answer first. And then they're going to give me a value of t and a value of the answer so that I can figure out what the plus c equals. But when I did this last time, see, I had this extra constant that shouldn't have been here. So this was wrong. This should have been negative 750 instead of negative 1 over 750. But here was the general answer first. And then when I plugged in their values, they gave me a 0 for t, and they gave me a 5,000 for the profit. And then my constant was wrong because I had the wrong constant. Here's what happened. So similar deal. We now know the regular function for profit. The integral of a derivative gives you the regular version. So this is the regular version, negative 1,000 e to the negative t squared over 4 plus c. This is what it is in general. I'm assuming t is going to be 0 again. Let's see. Yeah, t is 0, and it's not profit, it's population size. The population is 5,000 when t is 0. So that's still the same as the first time I did it. The population is 5,000 when t is 0. 0 is nice because 0 squared is 0. Negative 0 is the same thing as 0. 0 divided by 4 is 0. So then e to the 0 equals 1. And negative 1,000 times 1 is negative 1,000. So add 1,000. And the constant would be 6,000. So therefore, the population, I thought it was profit, but it's population. The original population function, not the derivative, the regular one, is negative 1,000 e to the negative t squared over 4. And now that I know the constant, 6,000 plus 6,000. So in other words, the population was 6,000 at the moment they started keeping track of time here. Okay, so, and I almost had it right except for I did the 1 over by accident, which shouldn't have been there. since it was an extra constant in the problem, not an extra constant in the du part. And as soon as I stopped the video last time, I didn't want to like waste time on the video trying to find the mistake. And as soon as I stopped it, then I realized what I did wrong, but it was too late to restart it at that point. Okay, so type an exact answer in terms of E. So we're going to leave that in there. And then now it worked. Okay. And when I got the answer wrong, it was I had 1 over what that shouldn't have been there. Okay, so that was the only issue. And now if you get that part right, now you can plug 6 months in. Since t is in months, yep, so then you just plug 6 in for t. A graphing calculator might help more for that. So negative 1,000 e raised to the, now if you plug 6 in, 6 squared is 36. 36 divided by 4 is 9, so it's just a little easier to type negative 9 rather than negative 36 over 4, plus 6,000. So I'm typing it in that way, and then they say round to the nearest person. So 5999.8, that would be about 6,000 people. So it seemed strange that it didn't seem to grow after 6 months. But that's just because e to the negative 9 isn't very large, so it's almost equal to 0. And doesn't change what the 6,000 is. You'd have to have a much larger t for it to make a difference. Okay, so now I have 100% on section 7.2. So now 7.3. 7.3 is leading up to what we do in section 7.4. And every math subject has a topic called the fundamental theorem of that math subject. There's a fundamental theorem of calculus, fundamental theorem of algebra, fundamental theorem of statistics. It's the most important rule that comes from the entire subject. And before we can teach you that, you need to see where it comes from, which is what section 7.3 is about. Okay, so I have an original function, f of x equals 2x plus 7. It's linear. And I want to go from 5 to 7. And I want to approximate the area under the graph and above the x-axis with 4 rectangles. Okay, so maybe, well, okay. Here's number 1. I have f of x equals 2x plus 7 from 5 to 7. Okay, so 2x plus 7, if you plug 5 into that, 10 plus 7 is 17. If you plug 7 in, 14 plus 7 is 24. So 17, when x is 5, the y is 17. When x is 7, the y was 24. 14 plus 7, 21. Okay, so we have a part of a line that's just going from 5 to 7, but if you kept going beyond that either way, it would go forever either way. In fact, this side, what would happen is it would come all the way back to the y-axis and it would cross right at 7. The y-intercept is 7. And then if you go up 2 over 1, up 2 over 1, over and over again, then you'll land here at 5 and here at 7. But what if I connect this up to the x-axis? And it's creating a trapezoid is what this is called, where you have 2 parallel sides, and then the other 2 sides are not parallel. So we have a trapezoidal area. We could actually figure out the exact area of this with geometry formulas, which we're actually going to do later in this homework assignment. But right now, what they're doing is they're trying to build up to what section 7.4 is doing. So what if, since they're going to tell you how many rectangles they want, and the more you do, the better the approximation will be. This first problem said n equals 4. N equals 4, that tells you how many rectangles they want you to do. Well, if I draw a line right where 6 would be, now I've got 2 rectangles. So what if I cut both of those in half? 1, 2, 3, 4 rectangles. I've got 4 rectangles that could approximate this area. And you can do it from the left or from the right. So they want you to do left first. These are what are called left endpoints. The left endpoint would be 5, 5.5, 6, and 6.5. And if I take the distance across where I'm going from 7 to 5, if you do 7 minus 5, that's your total distance across, and divide by how many rectangles you have, 4. This is 2/4 or 1/2. This is the width of each rectangle. The width of each rectangle is 1/2. Just based on, that's completely arbitrary based on how many rectangles you want to do. If I do a different amount of rectangles, it'll be a different width. Or if I go from different endpoints up here. So in this particular case, this is how it worked out, that the rectangles have a width of 1/2. And then you know that, hopefully you know in geometry, that the area of a rectangle is length times width. So the half distances are the width. The length of the rectangle is the function value at these spots. So if I go up to 5, or if I start when x is 5, then f of 5 is the height of what's going to be a rectangle right here that's only going to go like that. So you're just going to plug in f of 5, f of 5.5, f of 6, and f of 6.5. These will get you your 4 left heights. And then area is length times width, or base times height in essence. So every width or height, every width or base is 1/2. And then the heights are going to be different spots that we'll go to. So I need to figure out, and maybe you might want to make a table here, left endpoints. And then we're also going to do right endpoints. The left endpoints are 5, 5.5, 6, and 6.5. And then you have to figure out f of each of these. So I'll just put f of x right here. So f of x was 2x plus 7. So maybe you can do these quicker, but if you have to do a bunch of them, 2 times 5 plus 7, obviously that's 17. I haven't even pressed equal yet, but 2 times 5 plus 7 is 17. So that's how tall that first rectangle would be. Then if I change the 5 to I'll change it to a 6 first, just because I can type right over it. Now I got 19 for that one. Now I'm going to change the 6 to 5 insert 0.5. So that's 18. And maybe you can tell what's happening here. 17, 18, 19. This one's going to be 20. Well, the nice thing about the right endpoints is you're going to use all the same values except the first one. We're not going to use 5. We're going to use 7. Sorry, 7. So you already know the first 3 answers are 18, 19, 20. And then this one's probably going to be 21, because 2 times 7 is 14, plus 7 is 21. So the area estimation, the estimated area using left endpoints, you do 1/2 times each of these numbers added together. And the reason why, this is kind of the shortcut, the reason why this works is you're actually doing 1/2 times 17, plus 1/2 times 18, plus 1/2 times 19, plus 1/2 times 20. I'm adding up 4 separate areas, and each one is length times width. So it's 1/2 times this height, plus 1/2 times this height, 1/2 times this one, and 1/2 times that one. That's the left endpoints. For the right endpoints, you use this, 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 and this side of the rectangles. And because they all have the same width automatically by rule here, since we're going to make the width the same every time, then you can just factor out the width every time. So same thing with this one. This one's going to be 1/2. That's the width of all of them. And then all these added together. So we can add 18 plus 19 plus 20. 18 plus 19 plus 20 is 57. This is 57 right here. And this is 57. They always have those shared parts. Then 57 plus 17 is 74. Half of 74 is 37. But this one's going to be the 57 plus 21, which is 78. So this one's half of 78, which is 39. So the left endpoints are saying that the estimated average area is 37. The right endpoints are saying it's 39. So by left endpoints, I'm getting 37 for the estimated area. For right endpoints, I'm getting 39. And then you average those two. The average of 37 and 39 is 38. The average is the halfway point between them. Or you can do 37 plus 39 divided by 2 if you can't do it in your head. And then we can also do this by midpoints, and usually midpoints are more accurate than either the left endpoints or the right endpoints are. Sometimes the average of the left and the right might be better or worse than the midpoint. So for midpoints, what I'm going to do is I'm going to go halfway between each of these five values. So halfway between 5 and 5.5 is 5.25. 5.25. So let me make a column for this one. 5.25. Halfway between 5.5, think of that as like $5.50. The halfway point between $5.50 and $6 is $5.75. And then halfway between 6 and 6.50 is 6 1/4. Whoops, 6 1/4. And then halfway between 6 1/2 and 7 is 6 3/4. So instead of using 5, 5 1/2, 6, 6 1/2, or 5 1/2, 6, 6 1/2, 7, we're going to go in between them all and do 5 1/4, 5 3/4, 6 1/4, 6 7/4. So 2 times 5.25 plus 7. The first one is 17.5 for f of x. That would be the height of the rectangle at that spot. Then I can quickly hit second enter and change it to 5.75. Now I've got 18.5. Now when things are linear, you can see how the answers are going to go already. But 6.25 should give me a 19.5, yep. And then 20.5. So this estimated area would be 1/2 all of these added together. And usually the midpoint estimation is the best out of the left and the right. Although sometimes the average of the left and the right might be a little better than the midpoint method. So add this up and take half of it. Only because the intervals are a half. So, and this happens with linear too, that the answer I got here matches the average of the first two. If you're doing linears, the average of the left and the right will always equal the midpoint answer. Then we could actually use geometry, which is 1/2 times the height, which is the distance across the parallel sides, times both of the sides added together. That would be pretty easy to do here. And I think it would be 38 actually. The height of this trapezoid is 2, because the distance from 5 to 7 is 2. So there's a trapezoid formula in geometry, 1/2 height times base 1 plus base 2. So the height is 2 in this example. 2 times 1/2 cancels out. F of 5 would be the first base height, and F of 7 would be the second base's height. And the sum of those two is going to be the answer because the other part's canceled out. So 17 plus 21 is 38. So even in geometry, they would say this area is 38. So geometry says this exact area is 38. Now in calculus, sometimes we don't have graphs that match something from geometry. They're doing that on purpose here so that you can see where this is coming from. But later we'll get something like the original graph might be real wavy like this. And then we want to know how much area is there from here to here just arbitrarily. Well, there's no geometry formula that's going to figure this area out. There is nothing in geometry where you have one side that's all wavy like this. So then there's no geometrical way to do it. But if you get something that you recognize from geometry, like a rectangle, a square, a trapezoid, a circle, a triangle, then it's possible to use a geometry formula to get the exact answer. And that's where this all came from, was they did known ones where there's formulas from geometry, and then they could get the methods down first, doing the ones they know the answers to, and then they could do the ones that there was no geometry formula for them. Okay, now let's do a quadratic one. F of x is negative x squared plus 9. And we're going from -2 to +2. And again, they want 4 rectangles. N equals 4, but later they'll change that. And this one will actually be a little bit nicer for the width, because negative x squared plus 9, if I'm going from -2 to +2, which is totally arbitrary, but that's the one they gave me, and I want n equals 4, and again, that could have been 8 or 16 or 32 or any other amount. But if you go from the end minus the beginning, and that's actually a double negative, end minus beginning divided by the number of rectangles, this is the width of every rectangle. And it's nice when this comes out the way it's about to. 2 plus 2 is 4. 4 divided by 4 is 1. The width of every rectangle is going to be 1. Okay, so negative x squared plus 9 would have a 9y intercept, and it would be a parabola like so upside down, and it would actually cross the x-axis at 3 and -3. So we're not going to get all the way to the x-axis at -2 and +2, so it would be about here and here. So if we just arbitrarily stop at those 2 points, 2 and -2, how much area is there here? And there is no geometry formula for this. They don't have one for upside down parabolas. So we want to get 4 rectangles going from -2 all the way to +2. Well, they're each going to have a width of 1 because of this calculation right here. And that's pretty obvious, hopefully, in the graph, because if I remember how I broke that other one in half first, I went right halfway between them would be 0 here. That would give me 2 rectangles. And then if I go half again at 1 and -1, those are going to be my 4 rectangles. There's a rectangle from -2 to -1. There's another one from -1 to 0, then 0 to 1, and then 1 to 2. There's your 4 rectangles. They each have a width of 1, too. So if I do left endpoints, what you're technically doing is left endpoints, you're doing the width times f of the leftmost value here, plus the width times f of the next spot, -1, plus the width times f of 0, plus the width times f of 1. And if this was anything other than a 1, like last time it was a half, when it was a half, I pulled the half out, and then you had to multiply by half at the end. In essence, you're going to pull out a 1 and just do all the f ofs and add them together and multiply by 1. So in essence, with a 1, the 1 doesn't matter. So if I could figure out f of -2, f of -1, f of 0, and f of 1, these four added together will be the left endpoint estimation of the area. And f of 0 is easy, that's 9. F of 1 and -1 have the same answer because 1 or -1 squared are 1. And then this negative would turn them into -1s. -1 plus 9 is 8 for both of those. F of -2, -2 squared is 4, and then -4 plus 9 would be 5. So the left point estimation would be 5 plus 8 plus 9 plus 8 times 1, which the times 1 doesn't matter. So that's 14 plus 16, that's 30. The left endpoint approximation is 30 for the area. So the right endpoints are easy to do because you got 3 of the 4 answers done already. The right is exactly the same as the left, except you don't do this first one, but you do all 3 of these. And then you do this one instead at the end. So I'm going to need an f of -1, because I'm ignoring the times 1, plus f of 0, plus f of 1. Those 3 are the same I already did. And then I also need an f of 2, though. But f of 2 has the same answer that f of -2 has just because of the square. So that's going to be 5 also. So the left endpoint answer came from adding these 4 numbers together. The right endpoint answer is going to come from adding those 4 numbers together, but they are the same because the 5s balance out. So by coincidence here, the answers are the same. Not that they have to be, but here they turned out to be the same. And the average of 2 numbers that are the same is that number. So the average is definitely 30. 30 plus 30 divided by 2 is 30. Now the midpoint may not be the same as these 3 answers. Maybe it is, but maybe not. So now what I have to do is I have to get halfway between each of these. Halfway between -2 and -1 is -1.5. Halfway between -1 and 0 is -0.5. Halfway between 0 and 1 is 0.5. And halfway between 1 and 2 is 1.5. And the widths are still 1, so I can ignore that. Whatever f of -1.5 plus f of -0.5 plus f of 0.5 plus f of 1.5, whatever that adds up to, that's the midpoint approximation. And because we're squaring the numbers, 1.5 squared is the same thing as -1.5 squared. So once I do either 0.5 or 1.5, I'll have the other answer at the same time. So 1.5 squared is 2.25. And then if you make it a -2.25 and add 9, that's 6.75. So f of 1.5 and f of -1.5 will both have an answer of 6.75. And then if I do 0.5, 0.5 squared is -0.25 plus 9, that's 8.75. And then the -0.5 will have the same answer. So just the square helps to get, I have less work because I get 2 calculations instead of 4. So 8.75 times 2 plus 6.75 times 2 is only 24.25. So it's not the same as those other answers of 30. And this may be a better approximation of the actual answer. 24.25. 1.5. 0.5 squared. 0.25 negative 0.25 plus 9, 8.75. And then 1.5 squared. 9 minus that is 6.75 times 2. Oh yeah, I typed it wrong. Okay. So it's 17.5 plus 13.5. It's 31 actually. But I could have been safer if I would have just done 8.75 plus 6.75 plus 6.75 plus 8.75. I was trying to do it faster than that, but if I would have taken each individual answer and just added them together, I would have gotten it right. I tried to do it faster and messed up, so that's a warning to you. Very slow and steady wins the race, 31. But that could be a better estimation of the actual area. In fact, when we learn 7.4, we could come back and figure this out and see what the actual answer is. Okay, what if we do an exponential? E to the x plus 3. And it's still from -2 to 2, and we still want 4 rectangles. So that'll help because then our widths will each be 1. So number 3 is just like number 2, except the function's different. E to the x plus 3. But we're still going from -2 to 2, and we're still doing 4 rectangles. So that tells me the width is still 1. Each width is 1. So left endpoints are going to work the same way they did on problem number 2. I need to figure out f of -2, f of -1, f of 0, and f of +1 only. We don't go all the way to the 2. And each one of these will get multiplied by 1, and then you add them all up. The right endpoints, we're going to do the last 3 of these, -1, 0, and 1, plus 2 that we didn't do before. And then the midpoints are going to be -1.5, -0.5, +0.5, and 1.5. And anytime, oh no, I was thinking of the squared one. Okay, so we're going to have to do all 4 of these. So, and these are just going to be, how much do they want this rounded? Rounded 2 decimal places. Okay. So they're going to be all decimal approximations here because only e to the, not even that, e to the 0 is the only one that comes out nice. E to the 0 is 1, and 1 plus 3 is 4, so this is the only answer that comes out nice. The e to the 0. E to the 1 is itself, but e is 2.71828 and so on. So e to the 1 is e, and e plus 3 is just some approximation. E plus 3 is 5.718. So I'm going to write that down to 3 decimals, and then we'll round to 2 at the end. 5.718. E to the -1 is not the same answer because e to the -1 is not like, it's not like a square to the -1. So e to the -1, e to the -1 is 1 over e, what it's 1 divided by 2.7-ish. But I'll just type in e to the -1 and then add 3 to it. So 3.3678, so I'll make that an 8. And this is the same answer, 3.368. E to the -2. E to the -2 plus 3 is about 3.135. E squared plus 3 is 10.389. Okay, so the left endpoint, since all the widths are 1, I can just add this up and that'll be the answer. If the width wasn't 1, I would have to multiply by that too. So 3.135 plus 3.368 plus 4 plus 5.718. This is 16.221. So then I'm going to round it to 16.22. The left endpoint estimation is 16.22. Then the right endpoint estimation will be these four numbers added together. 3.368 plus 4 plus 5.718 plus 10.389. 23.475. So I'll bump that up to 48. 23.48. This is the right endpoint estimation. So the average of those two, 23.48 plus 16.22 divided by 2, the average of those two is 19.85. So left and right endpoints are rough estimations that usually one underestimates the answer and the other one overestimates it. And it's, I'll show you a picture here of what's going on, and you'll see in the underestimation, the bars are all below the curve. In the overestimation, they all stick out above the curve. So that's why the average is, if you're going to do left and right endpoints, because they're easier to do, it's good to average them to get a better approximation. Midpoints are one calculation that you can just get a good estimation from in one calculation instead of two, but they're harder to do because these X values are always weird. So unfortunately, I have to do all this all over again. E to the negative 1.5 plus 3. The first estimation is 3.223. And then if I do e to the negative 0.5 plus 3 is 3.606, except the next digit's 5 or higher, so I'll make it 607. E to the 0.5 plus 3 is 4.64. And then there's an 87 after that, so I'll make that a 9. E to the 1.5 plus 3 is 7.481, but after the 1 is a 6, so 482. 7.482 plus 4.649 plus 3.607 plus 3.223, 18.961. And so that would round to 18.96, which is fairly close to the 19.85 that we got for the average of the other two. So roughly, I would say the area is somewhere slightly less than 20. And we definitely wouldn't have a geometry formula that could do that problem. So we did linear, we did quadratic, we did exponential. Here comes a rational function. And they still want 4 rectangles, but the range goes from 1 to 9 now. So it's not going to be widths of 1 anymore. 3 divided by x plus 2 is the function. 3 divided by x plus 2. We're going from 1 to 9. And they still want 4 rectangles. So you need to do 9 minus 1 over 4. N minus beginning divided by the number of rectangles. 8 divided by 4. This means each width of each rectangle is 2 units. Okay, so for the left endpoints, you're going to start at the left endpoint here of 1. So I'm going to do f of 1, but then you have to go by 2s, so add 2 to that and you'll get f of 3. Add 2, f of 5. Add 2, f of 7. There's your 4 calculations. And you don't make it to 9 because you're doing the left endpoints. When you do the right endpoints, you're going to skip the 1 and do these next 3. So your first one will be the second one down here. 3, 5, and 7. And then this one will go all the way to 9. So the right endpoints always end at the end of the interval, and the left endpoints always start at the beginning of the intervals. And then the sum of these numbers have to be multiplied by 2 because that's the width. So I'll get all these and add them up, and then multiply by 2 since the width of every rectangle is 2. So f of 1 is easy. 3 divided by 1 is 3. 3 plus 2 is 5. F of 3 is easy. 3 divided by 3 is 1. Plus 2 is 3. Here's the first one that doesn't come out nice. 3 divided by 5 is 0.6. Plus 2 is 2.6. Exactly 2.6. The others are not going to be exact, and they want this rounded to 2 decimals again. So 3 divided by 7 is a big messy decimal, plus 2. So I'm going to round to 3 decimals so that I can do the end to 2. 2.4285 will be a 9. So if I do 2.429 plus 2.6 plus 8, this sum is 13.029. But then I have to multiply by 2 for the width of each rectangle. So the left estimated area is 26.058 or 26.06. And this 2.429 is also right here. That's the one nice thing is 3 of the answers get shared when you're doing left and right endpoints. So all I have is one calculation left. 3 divided by 9 is 0.33333, plus 2 is 2.33333. So add these 4 together and multiply by 2. 2.333 plus 2.429 plus 2.6 plus 3. The sum is 10.362. Times 2 for the width, 20.724, which will stay 20.72. Oops. So it appears this time the first one is an overestimation and the second one's an underestimation. So what's the average of those two? 2606 plus 20.72 divided by 2. The average is 23.39. And then if we do midpoints, this time the midpoints won't be so bad because the midpoint just means what's halfway between 1 and 3. Halfway between 1 and 3 is 2. Halfway between 3 and 5 is 4. Halfway between 5 and 7 is 6. Halfway between 7 and 9 is 8. So I need f of 2, f of 4, f of 6, and f of 8. Once you add these up, then you'll multiply these by 2 as well to get the midpoint estimation. So e to the 3 divided by 2 is 1.5, plus 2 is 3.5, so that one came out okay. Plug in a 4. 3/4 is 0.75 plus 2 is 2.75. 3 divided by 6 is exactly a half, so 2.5. So far I haven't needed a calculator yet. But 3 divided by 8, 3 divided by 8 is 3.75. Plus 2 is 2.375. So they all came out exactly. There was no long decimals, but I'll keep it to 3 places for now. Add these 4 answers together. 11.125 times 2 for the width is 22.25. So the midpoint estimation is 22.25. Okay, so let me see if do they show the graph here or not? Yeah, see, here's the graph. So I wanted to show you this real quick. Here they're doing the left endpoint. So this is a slightly different problem, but it's still from 1 to 9, and there's still 4 rectangles. So you can see there are rectangles drawn in here. So the left endpoints, you go all the way to where f of 1 would be. F of 1 on the curve is right there. So that's how you draw that rectangle. But see how it's sticking out? The curve is down here. There's a little white part. So in this example, the left endpoints are overestimating the answer because each rectangle, it goes to the height of the left side of the rectangle. F of 3 is taller than f of 5. So the rectangle is taller than the actual area would be. And same thing here. It's not quite as much of an error, but there's a lot of error right there. The white part is an overestimation of the answer. Then when you see the right endpoints graph, whenever I get to that, there it is. See how now the bars are all shorter than they were a second ago, because now you're going to f of 3 to determine the height, f of 5, f of 7, and f of 9. And now the curve is higher than the bars are. So that's an underestimation. And then when you do the midpoint, let's see if they have the midpoint graph here. Here's the midpoint graph. So now the height of the bars is the middle of the 1 to 3 range, which is 2. So now the height of the rectangle is 2. Or it's where f of 2 would be, I mean. So part of it sticks out, but there's also a part that's white. If you make that bigger, you can see it a little better. So those kind of balance each other out a little bit. This blue part seems to be a little bigger than that white part, but there's some balancing going on. So that's why the midpoint often is the best estimation. It's often better than even the average of these two. Okay, then what they want us to do is to do this again, but with geometry formulas, kind of like I did on problem number 1. And this is what we're leading up to in section 7.4. In 7.4, it turns out that if you do an integral from the start to the end, which we didn't have before, we never had numbers here before, but if you go from the start to the end and do your antiderivative, that equals the area under a curve. That's the big fundamental theorem of calculus. But in section 7.3, they're trying to prove it to you with all these rectangles and geometry formulas before they present it to you in the next section. Another thing, too, is on this number 5 problem, you might not recognize this in its format. This is back from college algebra. But in college algebra, if I have x squared plus y squared equals 16, yeah. That's the equation of a circle. This is a circle with a center of 0, 0, because there's no numbers in parentheses. And the radius is the square root of this number. This is a circle with a center of 0, 0, and it has a radius of 4. Well, if you solve for y, subtract the x squared over to the other side, take the square root, y equals plus or minus square root of 16 minus x squared. This is also the equation of a circle. It's just people don't recognize it because it's not in the proper format like this is. But this is a circle here, actually. And if you do the positive version only, the positive version is the top portion of the circle. The negative version is the bottom portion. In fact, in graphing calculators, there's a y equals button right up here in the top left, y equals. And that's why getting y equals in algebra is very important a lot of times. It's the best way to graph things. And if you wanted to do the graph in here, you wouldn't be able to unless you could solve for y. But I could put square root of 16 minus x squared. I've got y equals the square root of 16 minus x squared here. And let me check the window real quick. Okay, so then if I graph it, I'm going to get the top portion of a circle. And the axes are turned off. Let me put them back on. Axis on. Okay, graph. So there's a top portion of a circle only there, if you can see that. That's from just putting the positive version in. If I also go below y1, if I go to y2 and put negative square root of 16 minus x squared. Now it graphs both the bottom and the top of the circle, although it looks like they're disconnected, but that's just a graphics issue for the calculator, pixels and things like that. And it doesn't even look like a circle, it looks more like an oval shape, but that's the point I'm trying to make is that's what the plus or minus does. The plus is the top portion only, the minus is the bottom portion, and this is not a function because this fails the vertical line test. So the way they get around that problem is they give us the positive square root only. They didn't give me the plus and minus. So actually what I have here is integral from -4 to 0. And then they have the positive square root of 16 minus x squared. We're going to do this in section 7.4 actually as is. There's the antiderivative of this. But for now, they want you to use a geometrical formula, the formula of a circle. Circles have an area of pi r squared. That's a famous formula from geometry. And if I go from -4 to 0, this is -4 right here. These are the x values. When x is -4, you're right here. And when x is 0, then you're right there. This could have went from -4 all the way to +4, and then I would have had the entire top portion of the circle. Instead, I'm only doing this much. And definitely we wouldn't want to include the bottom of the circle because then it wouldn't be a function. But I could either go from -4 to 0 or all the way to -4, all the way to +4, or even stop at 2 or 3 or 1 or -2 or -1 or -3. So it's just arbitrary that they're making me go from -4 to 0. But actually that helps here because that's literally 1/4 of a circle. I'm doing 1/4 of a circle. And this circle has a radius of 4. So by geometry, the area of a full circle is pi r squared. This entire circle would have a 16 pi area, 16 pi area, but I'm only doing 1/4 of it, so mine has a 4 pi area. And then when we do this in section 7.4, we're going to just get an answer of 4 pi to this doing it all the antiderivative way. There's an antiderivative calculation you can do to figure this out. And that's the point here in section 7.3. They want you to get this answer from geometrical formulas to prove it to you that that's really the answer. Then in 7.4, you're going to do this the calculus way with the fundamental theorem of calculus, which was born from all this stuff about rectangles and geometrical formulas. So that's the whole point here is I'm not doing the calculus side of this yet. This is just 4 pi. I figured that out with a geometrical formula. And 2 plus x, this is similar to problem number 1. We're going from 1 to 5, 2 plus x dx. We're going to actually do this. In fact, I can show it to you now, since that's an easy one, but let me do the geometrical way first. So they want me to go from 1 to 5 for the linear equation 2 plus x dx. 1 to 5, yes. So remember problem number 1? It was a trapezoid. We had 2x plus 7, and we just happened to go from 5 to 7. That created a trapezoid. So and then this is the formula for area of a trapezoid in geometry. 1/2 height times the 2 bases added together. There should be a B2 right here. So that's what they want me to do on number 6, is just use the area of a trapezoid from geometry. And you could sketch a picture of this to show yourself that it is a trapezoid. F of 1 would be 3. So when x is 1, y is 3. That's where it starts. And then f of 5 would be 7. So 2, 3, 4, 5. 4, 5, 6, 7. So the line segment's just going that far because they limited me to 1 to 5. Connect up to the x-axis and you're getting a trapezoid. You could do what we did on problem number 1 and create 4 rectangles if you wanted to. You could go 2, 3, and 4 here. You could create 4 rectangles and do the left and right endpoints, the midpoints, the average of the left and the right. You could do all that if you wanted to. That's what we did in problem 1. So problem 6 is an easier way, actually, because this is a figure from geometry. There's already a formula for this. But the point of this chapter later is that you can do things that geometry can't do. Geometry, they need very special cases like circles or triangles or rectangles or trapezoids or anything else that there's formulas for. But most of the ones we do in calculus, there is no geometrical equivalent. Okay, so my height, the height is the distance between the parallel bases. So from here to there, that's the height. It's kind of a sideways height here. So 5 minus 1 is the height. This height is 4. And B1 and B2 is how tall each of these are, which is literally f of 1 and f of 5. And I already calculated them to figure out what the graph looked like. F of 1 was 3, and f of 5 was that 7 that I got already. So 3 plus 7 is 10, half of 4 is 2, 2 times 10 is 20. This would have an area of 20 by geometry. If I did it like problem number 1, remember in problem number 1, let's go back to that. The actual answer was 38. The left endpoint was 37. The right endpoint was 39. The average of that was 38. And the midpoint was 38. So if you did number 6 this same way we did number 1, that would be a very similar process. Your left endpoint and your right endpoint would be the same distance away from 20. Maybe they would be 1 away or 2 away. That you'd have to figure it out to tell for sure. They might not be 1 away just because the rectangle widths are different. So whether it's 19 and 21 or maybe 18 and 22 or something like that, the average would be 20 and the midpoint method would give you 20 also. Linear, the midpoint method always gives you the answer. Now, here's what you're going to learn next time in section 7.4 actually. I can show you this because you guys know how to do the antiderivative of this. The antiderivative of 2 plus x, the antiderivative of 2 is 2x. The antiderivative of x is x squared over 2. If you remember how you increase the exponent by 1 and divide by that new exponent. But then instead of putting plus c here, that's called an indefinite integral. If I do integral of 2 plus x dx with nothing here or here, this is called an indefinite integral. Indefinite. Then you put 2x plus x squared over 2 plus c. That's what section 7.1 and 7.2 are about. The section 7.4 is called definite integrals. And this is the fundamental theorem of calculus when there's numbers here. You have a range to go between. I'm going between 1 and 5. So the difference is you don't put a plus c at the end. You do the antiderivative the same way, 2x plus x squared over 2. But instead of putting plus c, we're going to evaluate this from 1 to 5. And what it amounts to is plugging in 5 and 1 and subtracting them. Somebody discovered that this works, and this is what's called the fundamental theorem of calculus. That if I want to know the area under the curve, I can either use a geometry formula to know it for sure, 20, or I can use estimations with left and right and midpoint rectangles and get an approximation of it. Or it turns out this gives you the exact answer too. F of 5 would be 10, and 5 squared is 25. 25 and a half is 12.5. So this is 22.5 for this part, minus f of 1 would be 2 times 1 would be 2, and 1 squared is 1, divided by 2 is a half. So this is 2.5 right here. 22.5 minus 2.5 is 20, see? That's what we got right here, 20. So now you can do anything. It doesn't have to be a geometry formula. any integral, if you can do the antiderivative of it and take the integral of it, if you plug in given range of numbers, you'll get the area under the curve. That's the whole point of section 7.3. 7.3 is trying to show you why what we're going to do in 7.4 works. And I just did an example for you. Okay, so lastly, we have two application problems where they want to do left and right endpoint rectangle method of estimating the answer, because we don't know how to find the antiderivative of this curvy thing. So, and then I think they have you average them too. It says, let the width of each rectangle be 2 hours. Okay, so if we're going to do left endpoints, we're going to start at the far left of the graph, then at midnight. So we have to estimate this, and it's a little hard to tell with this graph, but so the widths are 2, so I'm going to have 2 times for number 7. The left endpoints are going to be 2 times each of those heights added together. So I'm going to start at midnight. Whatever this height is right here, f of 0, if you call midnight 0, f of 0, it looks like that's about 9 right there. I'm going to estimate that as a 9. Then move 2 hours ahead of time because they said the widths are 2 hours. So go to 2 a.m. What's this right there? Now it's hard to tell. They want this rounded to the nearest whole number. Okay, so I guess I'll just go to the nearest whole number there and call that 10. I don't know how much leeway they're going to count off if I'm rounding too much too soon. Okay, another 2 hours would be 4 a.m. That one's pretty close to 11. Another 2 hours would be 6 a.m. Now we're up to, it looks like just about 12 exactly. So it's nice that at least they're keeping it close so that the rounding shouldn't be an issue. It's just we got a whole bunch of these to do because every 2 hours from midnight to midnight, there's going to be like 11 or 12 of these. So I'm up to 8 a.m. now. Unfortunately, that one looks like it's halfway in between. Okay, so I'm going to go, well, I don't know if I should put 14.5 or just round it to 15. Let's try 15 for now. And if it's wrong, then I'll put 14.5 for that. That one was hard to tell. It was halfway in between, roughly. Okay, 10 a.m. Again, that one's kind of halfway in between. But I'm going to go with 17 for now. Okay, noon. Since I've been going up every time, maybe I'll go down on this one and call this one 21. 2 p.m. That one looks like it's almost to this point, which would be 26. 4 p.m. That's exactly 27. 6 p.m. Maybe 26. 8 p.m. and 10 p.m. We have 2 left. 8 p.m. That one's 18. Whoops. And 8 p.m. No, I did that one already. 10 p.m. 10 p.m. is about there. 13. And we don't do midpoint or midnight because that's the right endpoint. That's where the right endpoints end. Oops, now I forgot what I had for an answer there. 10 p.m. was 13. Okay. 9 plus 10 plus 11 plus 12 plus 15 plus 17 plus 21 plus 26, 27, 26, 18, and 13. And then times 2. So my left estimate is 410. I don't know if I'm too lenient with that or if I should have done it a little closer, but 410. Let's see how strict they are on this. Okay, so I guess you can just do rough estimates like I was doing. That definitely helps. Okay, so then the right is the same thing. Oh, it didn't even want me to do the right. Okay, that's weird. I thought they were going to have me do left, right, and average, but they just wanted the left apparently. It does say left and right. That's weird, huh? Okay, well, that was weird. Maybe if you did the other one, maybe it comes out the same just by coincidence. So maybe each answer is the same no matter which way you do it. But if I would have done the right endpoints, I would have started at 2 a.m. instead of midnight, and I would have went 2 a.m. all the way to the next midnight. So the left endpoints, you don't use the second midnight. The right endpoints, you don't use the first midpoint, the first midnight. Okay, demand curve. Here's a demand curve from business. And our quantity is somewhere between 0 and 50. So there's my range to work between. And they want widths of 10. So number 8, last problem. We have a demand function from business. What's the demand for our product? It's a quadratic function, 1/10 q squared. Minus 10q plus 267, and we can make anywhere between 0 and 50 of our quantity every day of our product. And for whatever reason, they want width of 10. See how it's not always 4. So if you do end minus beginning of your interval and divide by how many rectangles, or how wide, either how many rectangles you want or the width of your rectangles, then you'll see that this is 5. Each one's going to have a width of 5. I'm sorry, yeah, I said the answer and wrote it wrong. So divide by 10, 50 divided by 10, the width is 5. So I'm going to go from 0 to 5, and then 5 to 10, and then 10 to 15, and that way I'll end up with 10 of those. Or maybe I'm misreading this. The width is supposed to be 10, not the number of rectangles. Okay, so yeah, I did that backwards. They already said the width was 10. So I didn't need to calculate this. What I just calculated was the number of rectangles. So this would work also if you want to know how many rectangles. There's going to be 5 rectangles, each have a width of 10. So 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 40 to 50. That's 5 of them. So we have some kind of quadratic function that goes like this. And I don't know where 0 or 50 would be, but let's just mark these spots arbitrarily. So 0 to 50, if I go 10, 20, 30, 40, and 50. There's your 5 rectangles, and they each have a width of 10. So this time the n was not 10. I misread that. N stands for the number of rectangles. N is 5 actually. But they told me the width was 10. So I could also use that to figure out how many rectangles there are in a same calculation. So if you do n minus beginning and divide either by the number of rectangles or by the width, then you get the other one of those two values. So each width is 10. And then if I'm going to do left endpoints, left endpoints are going to be 10 times. First you need f of 0, then f of 10, then f of 20, f of 30, and your last one will be f of 40. You won't make it all the way to 50. Add all those together and multiply by 10, and that's your estimation for left endpoints. For the right endpoints, you'll do 10, 20, 30, 40, and 50. You won't do 0, you'll do 50 instead. But once I figure out 10, 20, 30, and 40, I'll have them for both of these. So plug in Plug in 0. That's easy. When you plug 0 in, all this disappears except for the 267. 267. So f of 0 is 267. F of 10 will take more of a calculation. 1 divided by 10 times 10 squared minus 10 times 10 plus 267. So f of 10 came out to 177. And I wanted to do it in my graphing calculator because then I can do second enter and change all the 10s to 20s. Okay, so this one needs to be a 20 and this one needs to be a 20. So f of 20 is 107. Whoops, f of 30, change the two 20s to 30s. 57. It's kind of strange how they all end with 7. And f of 40 is 27. And I'm going to go ahead and do f of 50 right now just so I have it for the next part. F of 50 is 17. I don't need that one here. So I'm going to add up these 5 calculations. 267 plus 177 plus 107 plus 57 plus 27, and then multiply by the width of 10. So the area estimation for left endpoints is 6350. And that's in business, that's the money you'll make from the demand of your product. So the right endpoints, it still has a width of 10. But now you're not going to use the 267. Your first 4 answers will be these last 4 here. 177, 107, 57, 27, and then I already calculated it, so the other one is 17. But it's technically f of 50. So now add those 5 together. 177 plus 107 plus 57 plus 27 plus 17. Multiply this by 10, 3850. So apparently the first calculation is an overestimation, the second calculation is an underestimation. See, and this is what, remember those pictures in the examples? The left endpoints are having rectangles this tall. That's the first one. The second one comes all the way to here and goes over. The third one goes here and over. All this white area that's sticking out, that's an overestimation. The fourth one's there, and the fifth one is here. That's why the first answer is too large. When you do the second one, then the right endpoints, the rectangles are here, and here, and here, and so on. So they're all much smaller down, and now they're not covering all the area. There's part of the curve area that's not getting included in the rectangles. So that's why that one's an underestimation. 3850. And it's not that always that the left is an overestimation and the right is an underestimation. It depends which way the curve is going. So it depends if you're curving down or curving up, and how curved you are can make a difference in that too. So sometimes the left endpoints are the overestimation, sometimes the left endpoints are the underestimation. But if you do them both, whichever answer is bigger is obviously the overestimation. But since there's overestimating and underestimating going on, if I average these two, 6350 plus 3850, this kind of balances out. Not exactly, but it partially balances it out. So I got 5100 for the average. And I don't think they're going to make me do the midpoints here, but if I did, that might be a slightly better estimation. Okay, so we got 100% on section 7.3 now. And seven 3 is all done. 7.4 is coming up next. Fundamental theorem of calculus. And this, I showed you one example of it already. So when we start that video, you'll already understand what's happening there, hopefully. So see you next time for 7.4.